Now I want to introduce how a CPU works. I hope I can take away any fear of assembler you might have, because it's actually pretty simple. In the next video, you will be able to use this to crack your first small program. First, I had a very long script where I basically tried to develop the concepts of a CPU step by step, but I realized it's just too long and I didn't get the point across. But then I came across this hacking game by Starfighters.io. At the time of creating this video, Starfighters.io was not available yet. When you see this here, it should be up and running, so go and check that out. And the creators of that site have uploaded an article as a preview of the game. That preview is a fictional report of reversing a handheld device used for financial trading. And even though it's fictional, it's not far away from how it would look in reality. That's why I strongly recommend you to read it. But I will now take just the part where they introduce programming assembly and talk a little bit more around it. And then I hope you will understand how a CPU works. A CPU has amazingly simple concepts that can be used to solve very complex tasks. It's pretty crazy, and I hope you realize that by the end of the video. So imagine just a sheet of paper where you write instructions from the top to the bottom. This is your memory, like the RAM in your computer. And each line on that paper has a number assigned, just like a location in memory has an address. So instead of line 5 on a paper, in memory you would be something like address hex 4005db. So that paper, or your memory, contains the assembly code. But what can assembly code do? So first of all, you are given 8 to 32 global variables of fixed size to work with, and they are called registers. So your CPU, depending on your architecture, has a number of those registers. They call those registers global variables. And that's what they are. Just like in your C or Python programming, you can use them like variables. Store value in them and perform some arithmetics on them, like adding or multiplying. The next keyword here is fixed size. In a 32-bit machine, they are 32-bit wide. And in a 64-bit machine, they have 64 bits. So this is the biggest number you can store in one of those registers. And if you want to deal with bigger numbers, you obviously have to write code to split up the number over multiple registers. And some of those registers are special registers. The most important is the program counter, which tells the CPU which instructions we are executing next. Every time we execute an instruction, we advance the program counter. This register is often called PC, meaning program counter, but on our Intel x86 architecture, it's referred to as the instruction pointer, IP, or EIP, or RIP, depending on 60-bit, 32-bit, or 64-bit mode. So when you look at the paper with instruction in each line, the instruction pointer register will have the number of the line that will be executed next. We often also refer to this as pointing to, so the instruction pointer points to line 5. And when it has executed that instruction, it will increase by 1 to move it to the next line. Virtually all computation is expressed in terms of simple operations on registers. Let's do an example. In x86 assembler, you can move a number into a register, like move EAX 5. This means that EAX will now have the value 5. And then you can add a number like 3 to it. Add EAX 3. Now let's set another register to value 8. So move EBX 8. And then you can subtract those with sub EAX EBX. This means that EBX is subtracted from EAX and the result is stored in EAX. But real programs need many more than 32-bit 1-byte variables to work with. In our case of x86 architecture, that would be more than 16 registers with 64-bit, which is 8-byte. Imagine to write a game like Super Mario in assembly. You would have to store Mario's X and Y position, the lives, the enemies, the coins. You just need more than 16 variables. And when you want to collect more than 32-bit worth of coins, you need more space. Next point is, what doesn't fit in registers lives in memory. You can just use other parts of the paper where there's no assembly code to store more values. Makes sense, right? Memory is accessed either with loads and stores at addresses, as if it were a big array, or through push and pop operations on a stack. So the load and store instructions are called move in x86 assembler. So we can move values from a memory address into a register, and we can move value from a register into memory. I like Intel assembler syntax the most. So in this case, the brackets are like brackets from an array or list. So for example, in Python, to access a certain value in a list, you would write my list and in brackets 5 to get the element at index 5. So we just do basically the same, just with a very big number, because our RAM is very big. Also, they talk about push and pop operations on a stack. The stack is nothing else than just an area at the bottom of your memory, so like at the bottom of our paper. And then you have special registers that always point at the top of the stack. The stack pointer, SP or ESP or RSP. It's special, like the instruction pointer. And when you push a new value on top of the stack, for example push 5, the stack pointer will be incremented, pointing to the next address, and the value will be placed there. And when you do pop EAX, the value at the address of the stack pointer will be saved in the EAX register, and the stack pointer will be decremented. This is used in programs all the time. I have to correct myself. The stack is usually upside down, so the stack grows downwards, meaning it starts from the highest addresses, and when we push a value, we don't increment the stack pointer, we decrement it, and with pop, vice versa. But it doesn't really matter. Just imagine literally a stack where you put something on top or take something away. Memory is to an assembly program what the disk is to a Ruby or Python program. You pull things out of memory into variables, do things with them, and eventually put them back into memory. Now when we talk about efficiency and speed, the calculations on registers are super fast. And ideally, your whole program should only use registers. But because that's unlikely, you have to put values sometimes into memory, because you need those registers for more complex stuff. But if you would optimize your code, you would always want to make sure to access memory as little as possible. Well, this is also only half true, because you have something like caches near your CPU, actually multiple levels of caches, so if you repeatedly use a certain memory address, it will be cached in a special super fast memory near the CPU and not in RAM, which is not too bad, but you get the idea. Control flow is done via gotos, jumps, branches, or calls. The effect of these instructions is to alter the program counter directly. Control flow means that a CPU would be less useful if it would just execute your program line by line without being able to jump somewhere else. So for example, to repeat a task, you want to constantly jump back. In assembler, you have different instructions to do that. They are referred to as jumps, branches, or calls. And they all basically change the instruction pointer to a different value. So when you read jump 2, you would simply set the instruction pointer to 2 and continue with that line. Kind of like move EIP 2. A jump is just an unconditional goto. So when you encounter a jump, you will always follow it. But much more interesting for complex tasks is to make decisions what to calculate next. And most operations on registers like addition and subtraction have the side effect of altering status flags, like the last value computed resulted in 0. There are just a few status flags and they usually live in a special register. So for example, when we earlier added 3 to 5 with add EAX3, the result was bigger than 0, so the 0 flag would have been not set or simply 0. But when we subtract 8 from that with sub EAX8, the result will be 0 and thus enabling the 0 flag, setting it to 1. And branches are just gotos that are predicated on status flags like go to this address only if the last arithmetic operation resulted in 0. In x86 assembler, that would be the JE instruction, jump equal. Sounds weird, but how would you test if two values are equal? You can simply subtract them, and when the result is 0, they were equal and thus set a 0 flag. So it makes sense to call the branches 0 flag as set simply jump if equal. A caller is just an unconditional goto that pushes the next address on the stack, so a ret instruction can later pop it off and keep going where the call left off. So earlier I explained how the push and pop instruction works. So a very clever usage of the stack is this call instruction. Let's say in C you want to call a function. How would you do that in assembler? Especially because a function might be used in multiple places, so you always want to jump back where you came from. If you would just use the jump instruction, you would have to specify the exact address. So what you can do is use the call instruction instead. This will push the instruction pointer of the next instruction on the stack. And when the function you jump to finishes, it will execute the ret instruction. And ret will pop the current value on top of the stack into the instruction pointer again. So like pop EIP. So we can continue executing where we originally came from. And before we finish this video, I just want to make clear that assembler instructions are actually just numbers. As you know, a computer can only store ones and zeros, and we generally represent those as numbers. So assembler code doesn't actually say move EAX5, it will actually say B8050000, and hex B8 refers to move EAX. And the remaining numbers are available for the number you want to move into EAX. So when the hardware reads this number, it knows that it has to move the following number in its EAX register. And a disassembler is a software that takes this number B8 and makes readable text out of it for us to easier read assembler. If you want to try this out in practice, you can go to microcorruption.com. You have to use a debugger to solve different challenges. They also have a nice tutorial introduction to that debugger, and even though it's not x86 GDB, it has exactly the same concepts. And understanding concepts is way more valuable than mastering the technique, in my opinion. In the next video, we will use this knowledge to do a practical example where we will crack a small license check program.